All right, chapter 9 is on solids and fluids. All right, there are 4 states of matter. You've got solids, liquids, gases, and you have plasma. Plasma is more so out in space rather than a lot of it being on Earth. Now, you will see some sort of plasma lights if you're near the poles, either the North or the South poles, where the aurora lights are usually seen. Okay, so in the universe at large, the plasmas, these are the system of charged particles interacting electromagnetically, all right? But in our environment on Earth, we mostly have liquid, solids, and gases. All right, so a solid has a definite volume and shape. A liquid has a definite volume, but no definite shape. So it takes the shape of the container that it's in. And then gas has neither a definite volume nor a definite shape. Okay, so think of gas as like a vapor, liquid, think of water, and then solid, think of ice. So ice has a definite shape and volume. All right. So a solid is said to have elasticity. All right, so we talked about, I think, momentum in chapter 6, where we were talking about elastic and inelastic collisions. So during your elastic collisions, you have items or objects that retain their shape and volume and size. All right, so solids are classified to be either crystalline structures or amorphous. So your crystalline structures, these are ordered structure items. So this is like your table salt, your sugar, things of that nature. And then your amorphous solids, these are like items like glass and so on and so forth, where your items are arranged randomly. All right, so there's different types of matter. So the normal matter, which is what we see, it actually only takes up about 5% of all matter in the universe. All right, so there's existence of dark matter. Okay, so dark matter comprises 25% of matter in the universe. So this is several times larger than the normal matter that we are able to perceive with our eyes. And then we have the ever expanding and accelerating universe, which forms more mysterious matter, which they call dark energy. So that accounts for 70% of matter in the universe. So the deformation of solids, don't forget deformation means change in shape. All right, so although the solid is thought up of having a definite shape and volume, this can change, especially with external forces like collisions and things of that nature. All right, so large force can permanently deform or break an object. All right, when the external forces are removed, the objects tend to return to its original shape and size if it's said to be elastic. Okay, so inelastic objects, pretty much they're deformed forever, so their shape is changed forever. So if it's elastic, then it bounces back. If it's inelastic, then it doesn't bounce back shape wise. We also have stress and strain. Okay, so elastic properties of solids are discussed in terms of stress and strain. So stress is the force per unit area, also known as pressure. All right, so this can cause deformation as well. Strain is a measure of the amount of deformation or change in shape. So for small stresses, the stress is proportional to the strain with the constant of proportionality depending on the material. The elastic modulus, this is analogous to the spring constant. So for Hooke's law, we have the force is equal to the spring constant times the change in the spring itself. So whether that spring is stretched out or compressed to the smallest amount possible, or at its normal equilibrium. This is Hooke's laws, which is it's more geared towards springs. Tensile stress, again, this is the ratio of force over area. And we also call this pressure. So the force is in newtons, the area is in meters squared. Don't forget area is length times width. So that's why the meters is squared here. So newtons over meters squared is also called a Pascal. So Pascal is the SI unit for stress and or pressure. We also have tensile strain. So this is force over area, also known as pressure. And it's equal to Y, which is the proportionality constant that's sometimes called Young's modulus. So it varies from material to material. All right, so there's different forms of the equation. We have force is equal to springs constant again times the length of the spring or material. And K is also equal to Young's modulus times the area divided by the original length. So LO, it just means initial length or original length. All right, so again, pressure and stress, these are sometimes interchangeably used. They both mean force exerted over an area. And the SI unit for pressure again is pascals. So the density is the mass divided by the volume of an object. All right. So the SI unit for density is going to be kilograms, since that's the SI unit for mass and it's in the numerator. And then the SI unit for volume is meters cubed. So as we stated earlier, area is length times width, but volume is length times width times height. All right. So that's why the meters is cubed in the denominator for the volume. All right, so the density of water is nearly 1,000 kilograms over meters cubed. The density of ice is 917 kilograms over meters cubed. The density of air is 1.225, and the density of cooking oil is 870 to 920, depending on the type of oil. All right, so coconut oil will be different than olive oil or vegetable oil. So they all have their own individual densities. All right. So if you've ever had a glass of water, and let me go to the whiteboard right quick. All right, so this is our glass of water. All right, so let's say we have water in here and a couple of ice cubes. All right, our ice cubes are always going to float. It's always going to float on top of the liquid because of the density differences. All right, more dense, well, the substance that is more dense will sink. Can't write today. Dense will sink. And the less dense object, less dense, will float. Will float. All right, so if we go back to these numbers, we'll see that ice is 917, and then the water is 997. So let's go back, whiteboard once again. All right, the density of ice is 917 meters cubed. And then the water, and again, the density is denoted by the Greek letter rho. Rho. It looks like a P, but it's not a P. It's a Greek symbol. All right, so this is the symbol for density. And again, the SI unit for density is kilograms divided by meters cubed. All right, so since the water density, 997, is greater than 917, all right, your water is going to be here. Water will sink, ice floats, all right? So less dense floats, more dense sinks, all right? This is something that you need to keep in mind. You will see it again, all right? And if you've ever mixed oil and water before, all right, you'll notice that the cooking oil will always float on top of the water, and that is because it is less dense than the water. Another example of density differences is if you've ever gone to the beach or to a pool and you see the kids with the little flotation devices. They have the arms, they have the flotation things that you put on your arm. They have the loops that they sit inside. There's also a bunch of, different balls that they can play with in the water that are filled up with air. Because air is less dense than water, that is why they are able to stay afloat, okay? Because the air, which is 1.225 kilograms over meters cubed, is less dense than the water, which is nearly 1,000 kilograms over meters cubed, okay? More dense sinks, less dense floats. All right, so let's work out a couple problems. And let me see, how many do we have? So it's 2 on this slide, but I think there's a few more later. Okay. All right, a vertical beam in a building supports a load of 6 times 10 to the 4 newtons. If the length of the beam is 4 meters and the cross-sectional area is 8 times 10 to the minus third meters squared, find the distance the beam is compressed along its length. All right, so let's go ahead and go back up into the slides. So earlier we were talking about stress and strain, where we have force over area, which is our stress, equal to Young's modulus times the change in length over the original length. So they're asking us to solve for the change in length, which is delta L. So we will be using this equation and moving everything else to the other side of the equation. So let's go ahead and write this down. And let me clear this off. All right, so this is number 1. Okay, so we have force divided by area is equal to Young's modulus times the change in length over the original length. We want to solve for the change in length. That is our unknown variable. So let's move that to one side of the equation by itself. To do that, we would multiply by the original length and divide by Young's modulus. So let's do that to the other side as well. All right, divide by Young's modulus and multiply the original length. So that accounts for the original length and Young's modulus. So we'll end up with the change in length being equal to our force over area times the original length divided by Young's modulus. All right. So from here, we're just going to start plugging everything in. All right. For the force, they gave us, and let me scroll back down. For the force, they gave us 6 times 10 to the 4 newtons. And for the length of the beam, so this is the original length, is going to be 4 meters, and the cross-sectional area is 8 times 10 to the minus third meters squared. All right, so let's write all of that down. All right, so the force, again, that was 6 times 10 to the 4 newtons. Our original length was 4 meters. The area that they gave us was the 8 times 10 to the minus third meters squared. And then our Young's modulus, again, this is a constant depending on the material. And here they told us the material was made of steel. So what we would need to do is to scroll up in our book to find this Young's modulus for steel, which comes out to be 20 times 10 to the 10 pascals. All right, so once you plug all of this into your calculator, you would end up getting 1.5 times 10 to the minus 4 meters. All right, let's go on to number 2. A waterbed is 2 meters on the side and 30 centimeters deep. Find its weight for part A, and for part B, find the pressure that the bed exerts on the floor. Here's a hint right here. Assume the entire lower surface of the bed makes contact with the floor. Hint, use cross-sectional area, 4 meters squared, and the value of W from part A to get the pressure. All right, so let's go ahead, write down our unknowns. All right, so we're trying to find part A is the weight. And we know weight is mass times gravity. All right. So first we know what gravity is, right? Gravity is 9.8 meters per second squared. Now we need to find the mass of the bed, okay? They didn't give us a mass, so we have to find the mass. What they did give us was area, cross-sectional area, and they gave us the length and the width. So technically we can find the volume of the bed and use that. We know the density of water already, right? So we can use the density of water to find the mass. So let's go to the density equation, which is rho is equal to mass divided by volume. And we're trying to solve for mass. So we're going to move volume to the other side of the equation. All right. And we'll end up with mass being equal to the volume times the density of water. All right. So for the volume, that's length times width times height. So they already told us that the area was 4 meters squared. And then we had the depth of the bed, which was 30 centimeters. So we would have to convert that to meters, which is 0.3 meters. All right, and the density of water, we've already said was 997, but you can round that up to 1,000 kilograms over meters squared. And let me extend this. Kilograms over meters cubed, cubed. All right, so once you plug that into your calculator, you should end up with a mass of 1,200 kilograms. 1,200 kilograms. All right, now we can use this mass and plug it into the weight equation. All right, so now we're going to plug it into the weight equation. So weight is mass times gravity. So that's going to be 1,200 times 9.8 meters per second squared. All right, so our weight is going to be 1.18 times 10 to the 4 newtons. And then they told us for part B that we need to use the weight from part A to get the pressure. So pressure is force divided by area. So let's go back. All right, so pressure P is what we're trying to find now. So P is equal to force divided by area. All right, weight is a form of force. So what we can do is plug in the 1.18 times 10 to the 4 newtons. 1.18 times 10 to the 4 newtons. And put that over the area, which they told us was 4 meters squared. 4 meters squared. All right. And once you plug that into your calculator, you should end up with 2.95 times 10 to the third pascals. All right, so there are also variations of pressure with depth. So if you think about like the ocean, the further you go down into the water, the more pressure is being exerted on your body. Okay. So at the surface of the water, you're going to have less pressure than if you're scuba diving to, you know, the seafloor to see the coral reefs or something like that. All right, so when a fluid is at rest in a container, all portions of the fluid must be in static equilibrium. Furthermore, all points at the same depth must be at the same pressure. If this were not the case, fluid will flow from higher pressure regions to lower pressure regions. All right, so variation of pressure with depth. So pressure is P, and it's equal to the original pressure plus our density, which is rho. Okay, so it looks like a P, but it's not a P. This is the Greek letter rho. And we multiply that times the effect of gravity, which is 9.8 meters per second squared, times the height or depth of that pressure. All right, Pascal's principle. This just simply states that a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. Buoyancy force and Archimedes' principle. So this occurs when you have an object that is either partially or fully submerged into a liquid. All right. So the liquid puts a force on the object and the object puts a force on the liquid. All right. So that's what's called a buoyant force. All right. So it's the net force and pressure between the top and the bottom of the object. All right. So the buoyant force is denoted by capital letter B, and it's equal to the density of the fluid times the volume of the fluid times gravity. Okay, so this is what's known as Archimedes' principle. Surface tension, viscosity, and Reynolds number. So surface tension in the film of liquid is pretty much the magnitude of the surface tension force. All right, divided by the length along that force. So you have your viscosity. This refers to the internal friction of a fluid. So the viscosity of water is different from viscosity of honey or syrup. Okay, so it moves differently because of its own internal friction within those liquids. All right, so at sufficiently high velocities, fluid flow changes from simple streamline flow to turbulent flow. And this is where Reynolds number comes in. It is a dimensionless number. All right, and it's equal to the density times the velocity of the flow times d, which is either our distance of the tube divided by, and this is a constant, which actually depends on the fluid flow, the fluid type, right? All right, so this is the Greek symbol for eta. Kind of looks like a lowercase n, except the right side is hanging a little bit lower than the left side. All right, fluids and flow. Certain aspects of fluid and motion can be understood by assuming the fluid is non-viscous and incompressible in that motion. So your fluid rate through a pipe is usually constant across that cross-sectional area of the pipe at whatever speed that it's moving at is usually constant. But at any 2 points, you have the area of the first pipe or the initial pipe and velocity, and then equal to our area of the second and area times the velocity. All right, so this is the equation of continuity.